Welcome back to the Deep Dive. This is where we really get into the weeds on some big ideas.
Absolutely. And today we're tackling something, well, pretty massive. A theory that tries to unify basically all of physics.
Yeah, no small task.
Mhm.
We're looking at a paper called The Oscillatory Universe, a scale-invariant framework.
That's the one. And the central idea, I mean, it's bold. It suggests that everything, literally everything,
From the tiniest scales imaginable, like Planck length,
all the way out to the edge of the observable universe.
it all comes down to one single principle.
Oscillation, just
Yeah.
vibration happening across this immense fractal structure of scales.
Okay, a fractal structure. So our mission today for this deep dive is to figure out how that one idea oscillation is supposed to connect quantum mechanics with, say, gravity and cosmology.
Right. How does vibration explain, well, everything? The paper argues that things like scale are just, illusions. The only fundamental thing is the wave.
That's a huge claim. So where do we even start? What's the foundation?
It all comes back to a very familiar equation, actually, but used in a maybe unfamiliar way. It's the basic wave equation. V dollary equals lambda O by Y.
Velocity equals wavelength times frequency.
Oh, okay. I remember that from physics class. Light waves, sound waves.
Exactly. But here, the argument is much deeper. It's not just describing waves, it's defining reality itself. It's presented as scale-invariant universal.
Universally applicable. So if lambda isn't always the speed of light.
Not always.
Yeah.
The lambda is the characteristic velocity for whatever system you're looking at. So
Yeah.
yeah, for light, phi is just stay.
Okay.
But if you're talking about, say, planets orbiting a star, Vilar becomes the orbital velocity.
Ah, I see. And for matter, like an electron.
Then Vial relates to its de Broglie wave velocity, and lambda is the spatial size, the wavelength, and the 5 is the frequency, the rate it oscillates.
So if you know these wave properties for any system.
The theory says you understand its fundamental physics, because
Yeah.
physics is the oscillation. It emerges from it. But hang on, what about something that seems static, like an atom just sitting there? What's its characteristic velocity? It's not moving relative to me.
That's a great question. It forces us to think about velocity differently. It's not just about moving from point A to point B. It includes all the internal dynamics.
Internal dynamics.
Yeah, like the electron orbital velocities within the atom, the zero-point energy buzzing away at that scale, the speed information moves within the atom's structure.
So it's the velocity needed for the atom structure, its standing wave, to even exist and hold together.
Precisely. The universe isn't static at any level. This equation is meant to capture that inherent dynamism everywhere.
Okay, that changes things. It's not just movement through space, but the dynamics of space and structure itself.
And based on this, the paper proposes this fundamental trinity,
Right. The 3 basic ingredients for reality.
which are simply space, represented by wavelength lambda, time, represented by the period dollars, which is $1, and oscillation itself, the frequency of dollars.
So 5 equals 10 teradollars.
Yeah.
And the main equation gives us lambda VST, and $5 is lambda T. They define each other.
Exactly. And the really radical part is the claim that all the physical laws, all the constants we've discovered, like G for gravity or the fine structure constant.
They aren't just random numbers dialed into the universe.
No. The idea is they emerge directly from how these 3 things, space, time, oscillation, relate to each other across different scales. The complexity we see isn't fundamental. It's generated by this simple relationship playing out everywhere.
Okay, let's try to get a handle on the sheer scale we're talking about here, this cosmic scale map. If it unifies everything, how big is, well, everything?
It's almost impossible to really visualize. The numbers are just astronomical or maybe subatomic at the other end.
Huh? Right.
The theory maps reality across 61 orders of magnitude in length.
61. Okay, let's break that down. Where does it start and end?
It starts at the theoretical smallest possible length, the Planck length. That's 1035 meters, just incredibly tiny.
And the other end.
That's the size of the observable universe as we currently understand it, roughly 10 meters across.
Wow. So $1035 all the way up to
Right.
$10 plus $26. That's, 61 orders.
It
It's hard to even comprehend. Like, going from a single atom to the entire solar system is only about 20 orders. This is vastly bigger.
really is. And right away, that inverse relationship in VI dollars, lambda dot at S way, becomes obvious across this whole range.
How so?
Well, down at the tiny end, the Planck scale, $1035, things have incredibly small wavelengths, right?
Right.
Which means they must have incredibly high frequencies to maintain the characteristic velocity often stellar at those scales. We're talking frequencies around 10 to 40 hertz. oscillating unbelievably fast.
Okay, tiny size, super fast oscillation.
Mhm.
And at the other end, the whole universe.
It's the opposite. Massive size, 10 meters wavelength, so its characteristic frequency must be incredibly slow.
How slow?
Like 1026 hertz. One oscillation takes vastly longer than the current age of the universe.
So as size goes up, the oscillation rate, the frequency plummets. That's the basic rhythm.
That's the fundamental pattern the theory describes. Everything that exists is just a specific vibration, a specific harmonic within this enormous range.
Now here's something that really jumped out at me from the source. The geometric center of this huge scale.
Yeah, this is counterintuitive. We tend to think our scale, the human scale, like $100 meters, must be special, maybe central.
Because we're the observers.
Wait.
It feels like the middle.
But the math doesn't agree. If you find the geometric mean, not the arithmetic average, but the geometric mean between 1035 Vi and $10 plus $26.
And multiply them and take the square root, basically.
Right. You land somewhere around $10.455 meters.
And 10.455 meters is, what is that, about 30 micrometers?
Exactly. Roughly 30 microns, which is smack bang in the middle of the scale of biological cells, like a typical eukaryotic cell.
So the cell, not us, is the geometric center of the universe's entire scale range.
According to this framework, yes. The 10 to 5 meter scale. It sits perfectly balanced between the quantum world and the cosmological world.
And the paper says this isn't just a mathematical curiosity, it's significant. It's the point of maximum, what was it? Informational complexity.
Maximum informational complexity and dynamic entropy. That's the term used.
Why would complexity peak there at the cell scale?
Think about what's above and below it. Below you have the quantum realm, atoms, particles. They oscillate incredibly fast, right? So high computational speed, potentially, but they're structurally simple.
Okay, fast but simple, and above the cellular scale.
You get into larger structures, thus planets, stars, galaxies. They are structurally complex, much more stable over long times, but they are dynamically slow. Their frequencies are much lower.
Right, stable but slow.
The cellular scale, being in the geometric middle, gets the best of both worlds. It can tap into the computational speed of the quantum realm below it,
To process information quickly.
while also having enough structural stability, influenced by the slower macro scales above it, to maintain complex organization over time.
So it's like the perfect interface point, where the universe's basic hardware, the physical laws emerging from oscillation, can most efficiently generate software, which is biological computation, life itself.
That's the argument. It suggests life isn't an accident, but a geometric inevitability at this specific scale, where information density and dynamic stability are optimized.
It also makes sense why most of the universe isn't complex life. You know, the vastness of space, dark matter, the quantum foam, they're either too big and slow or too small and simple. Complexity is rare, concentrated in this middle zone.
Exactly. It's a peak on the complexity graph. And this idea of interconnected scales directly leads to another key concept, mirror symmetries.
Ah, the fractal part. Structures repeating themselves at vastly different sizes.
If the universe is truly a fractal oscillator, then the same fundamental patterns, the same ways of organizing energy and structure should echo across the scales. They're harmonics of the same underlying vibration.
The paper gives some pretty mind-bending examples, doesn't it?
It does. Get this. Electrons. Their structural scale is roughly 1018 meters.
Okay, tiny.
The theory points out that their dynamics, how they behave in fields, their binding patterns, mirror the dynamics of globular clusters.
Globular clusters. Those big balls of stars orbiting galaxies. What scale are they?
They operate around $10 plus 18 meters.
Wait, minus 18 and plus 18, that's 36 orders of magnitude difference.
36 orders. Yet, the paper argues the underlying mathematical description of their structure and energy binding shows the same form. It's a scale-invariant pattern.
That's hard to wrap your head around. An electron echoing a cluster of millions of stars. Any other examples?
Yes, one may be slightly easier to grasp.
Okay.
Atoms, around 10 meters.
Okay, atomic scale.
They are shown to have structural and dynamic similarities to galactic cores, the centers of galaxies, which operate around 10 plus 10 meters.
So 20 orders of magnitude this time. The way planets orbit a star or stars orbit a galactic center somehow mirrors electrons orbiting a nucleus.
It's about the fundamental pattern of how mass or charge organizes itself around a central point within an oscillatory system. The claim is it's the same wave mechanics playing out, just scaled up or down massively. It's not coincidence, it's resonance.
Okay, so space and structure are tied to scale and oscillation. What about time? This is where the theory gets really, really weird, right? Subjective time?
It does take a significant conceptual leap, yes. The idea is that our experience of time passing isn't universal, it's relative.
Relative not just because of speed, like in Einstein's relativity, but relative to scale.
Relative to the characteristic frequency of the system. Each scale, each structure experiences time, which the paper calls tau, at a rate determined by its own oscillation frequency, $5.
So my frequency is, let's say, roughly 1 hertz for my conscious processing or biological rhythm.
Right, so you experience about 1 second of subjective time for every 1 second of clock time that passes in the macroscopic world. Your ratio is 1-to-1.
But if I look at something much smaller, like a quantum particle, it has a vastly higher frequency, as we discussed.
Orders and orders of magnitude higher, which means, according to this theory, its subjective experience of time is massively dilated compared to ours.
Dilated how? Faster? Slower?
It experiences more subjective time passing for every second of our time, way more.
Okay, more time passes for faster frequency objects. And this is supposed to explain quantum mechanics.
Oh.
Like the double slit experiment.
This is presented as the key insight, the aha moment, that potentially dissolves quantum paradoxes like superposition or wave function collapse.
We claim. How does it work? In the standard double slit, the weird part is the particle seems to go through both slits at once to create the interference pattern.
Right. Standard QM says it exists in a superposition of states until measured. This theory says, no, the particle, I use a photon, scale around 10-15 meters definitely goes through only one of the slits. Physically.
Okay, so no superposition. Then where does the interference pattern come from? How does it know about the other slit?
It knows because of time. Subjective time. When we run the experiment, how long does the photon take to fly from the emitter to the detector screen in our lab frame?
Practically no time. A nanosecond. Maybe less.
Exactly, a tiny fraction of a second for us. But for the photon, with its incredibly high characteristic frequency.
A huge amount of its own time passes during that nanosecond.
An almost inconceivable amount. The paper calculates that for something at the electron or photon scale, during 1 second of our time, it experiences something like 199 billion years of its own subjective time.
Wait, 1 billion years passing for the photon while only a nanosecond passes for us?
That's the implication of the scale-frequency-time relationship.
Okay, mind blown. But how does that create the interference pattern on the screen?
It's called temporal integration. During that incredibly long subjective lifespan, billions of years condensed into our nanosecond, the single photon interacts sequentially with the electromagnetic environment of the entire experiment setup.
Sequentially. Meaning, over its long subjective time, it feels the influence of the slit it didn't go through.
Precisely. It has more than enough subjective time to effectively scan or interact with the standing wave patterns set up by both slits, even though its physical path is through just one. It explores the whole wave potential of the system over its internal time.
So the interference pattern we see isn't from the photon being in two places at once spatially.
It's the accumulated result, the integral of all those interactions over its vast temporal experience projected onto the screen at the end of its journey.
Wow. So wave-particle duality isn't about the particle being a wave and a particle simultaneously.
It's about the particle experiencing enough subjective time to interact with the wave-like potential of its environment. The duality is a result of the vast difference in temporal bandwidth between the quantum object and the macroscopic observer.
And what we call wave function collapse when we measure it.
It's just the moment its integrated temporal history becomes fixed on the detector. No spooky instantaneous action needed. It removes the need for non-locality in that sense.
Okay, if that's true, it should also explain why we don't see quantum interference with everyday objects, right? Why doesn't a baseball diffract through a doorway?
Exactly. It comes down to that subjective time bandwidth again. Larger objects have much lower characteristic frequencies.
We saw that bigger scale, slower frequency.
Right, so let's look at the numbers again. An electron, 1018 Nars, gets 199 subjective years per arcsecond. Massive bandwidth.
Okay.
An atom, $10 is already much slower. Its frequency gives it maybe 10480 per 10,000 subjective years per arcsecond. Still a lot, but way less bandwidth.
Huge drop. And a baseball, or us. at $100 meters.
Our frequency matches the observer's frequency, 1 subjective second per 1 observer second. Essentially 0 extra time bandwidth compared to the experiment's duration.
So if you fire a baseball through a large double slit, during the fraction of a second it takes to travel, it experiences only that fraction of a second subjectively.
Right. It simply doesn't have the time in its own frame to interact sequentially with the whole setup and build up an interference pattern. It just acts like a classical object following a single path.
So quantum behavior fades out with increasing size because the subjective time available during an experiment becomes insufficient. It's not just about size, it's about the time crunch relative to frequency.
That's the core idea. Quantum weirdness is a consequence of extreme time dilation at small scales.
This is radically reshaping things.
Yeah.
Now let's move on to forces. Gravity, electromagnetism, the nuclear forces, how do they fit into this oscillatory framework? The paper says no force-carrying particles.
Correct. It dispenses with the idea of fundamental bosons like photons or gluons or hypothetical gravitons being the source of forces. Instead, it defines forces differently. As dimensional flows. Forces are seen as essentially information gradients. They arise from the flow of energy, or maybe coherence, across the boundaries between different scales in that 61-order hierarchy.
Information flowing between scales, like from the atomic scale to the molecular scale.
Yeah, exactly. Or from the Planck scale up to the macroscopic scale. These flows are bidirectional up and down the scale ladder, and the force we perceive is the effect of this informational pressure or gradient.
Okay, that's abstract. How does that explain something concrete like? Why is gravity so incredibly weak compared to the other forces? The hierarchy problem.
This framework offers a potential solution that's become quite well known from this paper. It says, gravity isn't fundamentally weak, it's distant.
Distant in terms of scale.
Yes. Gravity, the force that shapes galaxies and holds us to the Earth, is defined as an informational flow that originates way down at the bottom of the scale ladder.
At the Planck scale, 1035 meters.
That's the idea. It flows upwards from the Planck scale, crossing scale boundary after scale boundary, to eventually influence things at our macroscopic scale, $100 and beyond.
So the signal for gravity has to travel across how many scales?
Roughly 35 orders of magnitude just to get from Planck to us. Think Planck scale, quarks, protons, neutrons, atoms, molecules last with us.
That's a lot of steps.
Imagine trying to get a message through 35 layers of soundproofing. Each boundary, each scale transition filters or slightly scrambles the information, reducing its coherence.
So the gravity we feel isn't the true strength of the oscillation at the Planck scale.
It's the incredibly faint, filtered echo of that oscillation after it's been attenuated by passing through dozens of dimensional layers. Its weakness is a measure of the distance it had to travel up the scale hierarchy.
That's an elegant idea. Does it hold up for the other forces? Are they closer?
The source material presents data showing a strong correlation. Let's take the strong nuclear force, the strongest one we know.
Holds atomic nuclei together.
Right. It operates primarily between the Planck scale and the scale of quarks protons, roughly 10, 18 meters. That's only about, say, 17 orders of magnitude it needs to cross.
Okay, 17 steps versus gravity's 35 plus drum.
And its relative strength is huge, around $10 compared to gravity is 1.
What about the electromagnetic force?
That mediates interactions from the quantum scale up to the atomic and molecular scale, maybe 8 or so orders of magnitude involved in typical chemical interactions.
And its strength is around 10, 12. Still enormous, but slightly less than the strong force.
The pattern seems clear in the data presented. Fewer scale transitions correlates with greater perceived force strength. Strong force. $1 approx $17,000, strength approx $10, I dollars towns, $19 EM force. 1 approx 88, strength approx 35 plus $1, strength approx 881.
Wow. So the weak nuclear force fits in there too.
Yes, its short range means very few scale transitions, correlating with its significant strength relative to gravity, though less than EM and strong. It provides a unified picture based on informational distance.
Okay, if gravity is information flowing up from the Planck scale, what about flows coming down? This ties into dark matter, doesn't it?
It does, and it offers a completely different explanation for dark matter, one that doesn't require finding new exotic particles here in our labs.
So what is dark matter in this view?
It's essentially the gravitational influence, the pressure, flowing downwards from the very largest scales of the universe. The cosmic web, the superclusters, operating way up at 10 meters.
Slowing down onto the smaller scales where we see its effects, like individual galaxies.
Exactly. Galaxies feel the gravitational weight or influence of the colossal structures they are embedded within, structures maybe 5 orders of magnitude larger.
So the extra mass needed to explain galaxy rotation curves isn't missing matter within the galaxy?
It's the external pressure or gravitational tide from the megastructures surrounding it, like an atom feeling the forces from the molecule it's part of, even though it can't see the whole molecule.
The galaxy is feeling the pull of the cosmic web it lives in.
That's the idea. It feels this large-scale influence as if there were extra invisible mass locally. But the source is cosmological, not particulate.
And this leads to a very specific testable prediction regarding dark matter searches.
It does, a crucial one. If this theory is right, then all the experiments currently running deep underground, trying to detect hypothetical dark matter particles like WIMPs or axions, bumping into their detectors.
They will fail.
They should fail because they're looking for the wrong thing in the wrong place. The missing mass effect isn't caused by local particles, it's the integrated gravitational influence from structures vastly larger than our galaxy.
That's a bold prediction against a major area of experimental physics.
It is. Now let's jump back down to the other end of the scale. The Planck length, 1035 meters. Physics usually hits a wall there, right, where our theories break down.
Yeah, the singularity problem.
Yeah.
General relativity and quantum mechanics give nonsensical answers.
This theory reframes that wall. The Planck scale isn't an endpoint, it's a mirror.
A mirror. What does that mean?
It means the fractal geometry of the universe has to be closed, topologically. If you try to go below the Planck length, you don't hit zero or infinity.
You loop back around.
You loop back, effectively connecting to the largest scales, $10, but in a different layer, or perhaps a different phase of the universal fractal. The smallest scale reflects the largest scale.
So the hierarchy isn't just a line. It's more like a circle or a spiral,
Something like that. And this has profound implications for black holes.
which are usually seen as singularities where information is lost.
In this view, they aren't singularities in the traditional sense, they're dimensional transition zones. When enough mass collapses, the gravitational flow intensifies enormously.
The flow up from the Planck scale we talked about earlier.
Well, the collapse creates intense pressure down towards the Planck scale. The event horizon is the point where matter is forced through that Planck mirror.
Forced into the 1035 meters scale, and then what?
It transitions. As the wavelength goes towards the Planck minimum, the frequency must skyrocket towards the Planck maximum, 10 terts, to maintain the characteristic velocity relation. Matter essentially dissolves into its highest frequency, most fundamental oscillatory form.
And the information. Is it lost?
No, it's transcoded. The information isn't destroyed, but its form changes radically. It passes through the mirror and potentially reemerges as new structure, perhaps contributing to the large-scale fabric in that other layer connected through the mirror. Information is conserved, just transformed.
Okay, we've dealt with the smallest scales and black holes. What about the very beginning, the Big Bang? How does an oscillatory universe begin?
It reinterprets the Big Bang significantly. It wasn't an explosion from a single point, a singularity. That model has issues, like the horizon problem.
All right, how could opposite sides of the universe be the same temperature if they were never in causal contact after the initial moment?
The oscillatory universe suggests the Big Bang was more like a phase transition. Imagine the entire proto-universe as a uniform field, like supercooled water ready to change state.
Okay.
The bang was the moment this field underwent a rapid phase transition, like the water suddenly freezing into ice. But critically, it didn't start freezing from one central point.
It started freezing everywhere at once, or from many points.
From many nucleation points scattered throughout the field, all triggered simultaneously by a shift in the overall cosmic oscillation parameters, like ice crystals forming independently but synchronously across the water's surface.
Ah, so different regions didn't need to be in contact after the transition started.
Because they all emerged from the same initial state, undergoing the same synchronized transition. They naturally inherited the same properties, the same temperature. That solves the horizon problem quite elegantly.
And does this crystallization idea explain anything else?
Yes, the large-scale structure we see today, the cosmic web, with its filaments and voids,
Oh.
those structures could be the natural result of these different crystal domains expanding and meeting each other. The filaments are where the domains push together, the voids are the spaces in between. It's the pattern you'd expect from a cooling and solidifying process with multiple starting points.
Okay, that makes intuitive sense. If the universe is this giant oscillator, can we figure out its current rhythm, its fundamental frequency right now?
We can estimate it using the core equation, v dollars st Adroloio. We take the characteristic velocity v as the speed of light, and the characteristic wavelength lambda as the radius of the observable universe, roughly $10 meters.
Okay, plug those in. What frequency $5 do you get?
You get an incredibly low frequency, as we noted before. It comes out to about $3 times 1018 hertz.
$3 times 1018 hertz. So what's the period of one full cycle? That's $1.
If you calculate $1, 3 times 1018, it works out to roughly 3 times 1017 seconds. Convert that to years.
And it's around 10 billion years. One cosmic beat takes about 10 billion years.
That's the calculation based on this model, and the current accepted age of the universe is about 13.8 billion years.
So if one cycle is 10 billion years, and the universe is 13.8 billion years old.
We are approximately 1.4 cycles into the current cosmic oscillation. We're living in the second beat of the universe's rhythm.
The second beat? Wow. Our entire cosmic history from the Big Bang phase transition until now is just over one full breath of the universe.
Puts things in perspective, doesn't it? We're past the initial inhale, maybe in the first part of the exhale, definitely.
Hey, one more major quantum mystery. Entanglement. Spooky action at a distance. How does measuring one particle instantly affect its partner even light years away?
Standard physics struggles with this, invoking non-locality. But the oscillatory universe offers a different perspective, again avoiding faster-than-light signaling.
How? If they aren't sending signals, how do they stay coordinated?
The coordination isn't between the particles across space. It's because both particles are locked into the same underlying rhythm. They are phase coherent.
Phase coherent mean...
Remember the fractal hierarchy?
Yeah.
All scales, from the Planck frequency, 10 hertz, down to the cosmic frequency, 10 hertz, are coupled. They resonate together like harmonics on a single giant instrument.
Okay, the whole universe is humming together.
So two entangled particles, no matter how far apart, aren't connected by some invisible thread. They are simply two expressions, 2 points on the universal wave field that were created with the exact same phase relationship relative to the fundamental Planck oscillation.
Like two metronomes started at the exact same time and set to the same beat.
A good analogy. If you change the setting on the master beat, which you can't really do, but imagine observing the phase, both metronomes instantly reflect that change, not because they communicated, but because they are both driven by the same underlying rhythm.
So when we measure one entangled particle and find its spin is up, its partner is instantly down because they were always just perfectly anti-correlated expressions of the same fundamental wave patterns phase.
Exactly. Their states are correlated because they share a common origin and are both resonating with the same universal frequency hierarchy. No spooky action, just shared phase coherence.
All right, let's try to pull all this together. The implications here are, well, they fundamentally change our picture of reality if this framework holds true.
They really do. We have to reconsider some very basic assumptions, like the idea of solid particles.
Gone. Replaced by standing waves or localized oscillations.
Right. And fundamental forces.
Also gone. Replaced by these informational flows or pressure gradients across scale boundaries.
And even the distinction between matter and energy
becomes just a difference in the amplitude of the oscillation. High amplitude, stable oscillation looks like matter. Lower, less coherent amplitude looks like energy.
That's the essence of it. Everything boils down to vibration. The wave is the fundamental reality.
And the apparent differences due to size, due to scale.
That's the illusion. Scale is just the parameter that determines the frequency and complexity, but the underlying principle is the same everywhere.
Which brings us back to us, human consciousness. How do we fit into this symphony of frequencies?
Well, our conscious experience, the processing speed of our thoughts, our brain waves, they operate in a specific frequency band, don't they?
Yeah, typically measured between, say, 1 hertz and maybe 100 hertz for faster gamma waves.
The theory proposes that this isn't arbitrary, that 100 hertz range is special. It's identified as a harmonic convergence point.
Harmonic convergence, meaning?
Meaning it's a frequency band where information coming up from the incredibly fast, high-frequency quantum scales below us
can be effectively sampled or down-converted.
and coherently synchronized with information coming down from the much slower, large-scale, stable structures above us, our bodies, our environment, the planet.
So our minds operate at the frequency that's best suited to integrate information from both the micro and macro worlds.
It's presented as the optimal frequency band for complex, integrated self-awareness within this oscillatory framework. We're uniquely positioned in the frequency spectrum.
And this connects back to why the cellular scale, Tyndall's, was the geometric center.
Exactly. Life emerges there because it's the scale that balances the quantum speed needed for computation with the macro stability needed for structure and memory. Consciousness, as we know it, operating around tens of hertz, might be the natural frequency for processing the information available at that central cellular scale.
The system naturally finds the optimal point for complex processing.
It also leads to some fun, if speculative, thought experiments about consciousness at other scales.
Like what?
Imagine, hypothetically, a consciousness emerging at the scale of a planet, say, 107 to 7 meters.
Okay, planetary mind.
Given the inverse relationship between scale and frequency, its characteristic frequency would be incredibly low, maybe 10·7 hertz.
So one cycle every 10 million seconds. That's
Yes.
one thought every few months. Or one thought per day, roughly.
Something like that. An incredibly slow, ponderous consciousness. And conversely, imagine a consciousness at the molecular scale. It would have perhaps 10-12 thoughts per second, incomprehensibly fast for us.
So our 1/100 hertz is this human speed of thought, maybe the most effective for interacting with reality as we perceive it. The middle ground.
The temporal sweet spot for relatable active awareness. Now, crucially, this isn't just philosophy. The paper proposes concrete, testable predictions.
Right, that's what makes it science, potentially. What are some key experiments we could do? Especially those based on the subjective time idea for quantum mechanics.
Okay, prediction 1 for QM. Take the standard double-slit experiment. We need to modify it by using ultra-fast shutters.
Shutters that open and close incredibly quickly, like femtosecond scale.
Yes. The idea is to reduce the time the particle has to fly through the slits and interact with the fields. If the shutter time becomes shorter than the minimum subjective time the particle needs to feel out both slits,
Then the interference pattern should get weaker, or even disappear entirely.
exactly, you're cutting off its subjective time budget. Less time, less interference. That would be direct evidence for the temporal integration idea.
Okay, that seems feasible with current tech. What's another QM prediction?
It relates to doing interference experiments with larger, more complex particles. Things like buckyballs, C60 molecules. They're much bigger and heavier than electrons.
And therefore have a lower characteristic frequency and less subjective time bandwidth.
Correct. So the prediction is to get clear interference patterns with buckyballs, you actually need to make the experimental apparatus longer. You need to give them a longer flight path from source to detector.
Longer path. Why?
To give them more macroscopic time during their flight. Even though their subjective time runs slower, giving them more clock time allows them to accumulate just enough internal subjective time to perform the necessary sequential interactions for interference.
So, counterintuitively, you need a bigger setup for bigger particles to see quantum effects because they need more clock time to make up for their slower internal time.
Precisely. It flips the usual intuition. It's about providing sufficient temporal budget, not just spatial arrangements.
Fascinating. What about predictions at the other end, cosmology? Testing the dark matter idea as downward pressure.
If dark matter is this top-down flow from large-scale structures, $10 onto galaxy clusters, $1021, it should imprint a specific signature on those clusters.
What kind of signature?
Instead of galaxy clusters having smooth, gradually fading halos of dark matter, as predicted by particle models.
They should have sharper edges.
Yes. The theory predicts more defined boundaries, almost like biological tissues or cells having membranes. These sharp edges would represent the boundary interaction zone where the pressure from the larger scale structure meets the cluster's own scale. It would look more organized and less fuzzy.
So mapping cluster edges with high precision could test this. And the Big Bang prediction, the phase transition.
If the universe crystallized from multiple nucleation points, the cosmic microwave background radiation, CMB, the afterglow of the Big Bang, shouldn't be perfectly smooth, even after accounting for known fluctuations.
It should have subtle marks left over.
It should retain faint geometric patterns, like seams or fault lines, where these different crystallization domains met and merged in the very early universe. Detecting those specific geometric signatures in the CMB data would strongly support the phase transition model over a single-point explosion. #outro.
Okay, we have covered a lot of ground. From $5, lambda Chugata update way to the structure of the cosmos. This oscillatory universe theory, it really does attempt to weave everything together with just that one thread. vibration.
It's incredibly ambitious, redefining particles, forces, matter, energy, even time itself, all as aspects of oscillation across a vast 61-order fractal hierarchy.
Connecting the dance of atoms to the structure of galaxy clusters. It's quite a picture.
And that core message from the source material really sticks with you, doesn't it?
It does. Let's say it again. Pattern is the only permanence.
Scale is the only illusion.
Wave is the only truth.
It's a powerful summary of a radically different way to view reality.
Absolutely. And it leaves us, and you, with a final thought to chew on. We calculated that we're about 1.4 cycles into the current cosmic oscillation, living the second beat.
Right. So if this oscillation is ongoing, cyclical, think about the structures above us, those megaclusters, the cosmic web, operating at their own incredibly slow frequencies.
What about them?
Could they be setting the tempo for what comes next? Could the dark matter pressure we feel be, in some sense, the leading edge of the next major cosmic phase transition? Are those giant slow oscillators subtly guiding our universe towards its next state?
Are we feeling the first hints of the third beat beginning? That's definitely provocative, something to ponder.
Indeed.
Yeah.
Is the symphony already changing tune on a scale we can barely perceive?
We hope this deep dive has given you a lot to think about, a new lens perhaps, on the vibrating reality we inhabit. Thanks for joining us.